Let's take a look at this example so that we can see this difference between exponential functions and linear functions. We've done a lot of work with linear functions and applications of them. So what we want to do is see what kind of different wording shows up when we're dealing with an exponential function so that we know which model to use. So we have company A. So company A has 100 stores and expands by opening 50 new stores a year. Company B has 100 stores also and expands by increasing the number of stores by 50% each year. Write an equation for each company expressing their total number of stores per year. So already we can see this difference of company A's increasing by a count of 50 new stores, where company B is increasing by a percentage of new stores. So what we're going to do here is let's make a table of values and see how they behave. So over on this left-hand side, I'm going to write information for company A, and on the right-hand side, let's look at company B. So company A, let's make an X and Y table where X will represent, let's see, we're working by years. So X will represent the number of years that have passed. And then what we're going to do is look at the total number of stores they have. So in year 0, company A had 100 stores. Then it's increasing by 50 stores each year. So in year 1, we would have 150. So the change that I used there was just adding 50. Then year 2, we would have 200. So again, that would be coming from adding 50 on again. So it'd be like 100 plus 2 times 50 would get us there. And then year 3, we would have 250. So that's coming from starting at 100 and adding on 50 3 times. And this is where we start seeing our linear behavior. We always have that fixed amount of 100, but then depending on how many years have passed, that's how many times we want to add 50. So this behavior right here is linear because that rate of change is coming from adding the same number over and over. So the amount of stores for company A, we would take 100 plus 50 times X, and that's how we would calculate it. So company B, let's see the behavior here, kind of looking at those same years 0 through 3, and see if we can get an idea of the behavior that's occurring. So I'm going to have X and Y on my table. We're going to look at year 0, 1, 2, 3. So in year 0, we have 100 stores. So we have this idea of initial value for both of these. This company A, that initial value is what's working as our y-intercept. Same thing here, we have this initial value. It's also a y-intercept here. It's just not going to fit the y equals mx plus b form. Okay, when we go to year 1, what we want to think of is how we're changing is we want to take 100 plus 50% of that last number. So to take 50%, I'm going to do 0.5 times 100. So 100 plus 0.5 times 100 is 150. So it actually looks like we added on the same amount there, but just notice that in terms of a calculation, it came from a calculation. Or it came from a percentage. There we go. What I wrote here with this 100 plus 0.5 times 100, I can shorten that notation, and it's like I have 1 times 100 plus 0.5 times 100. So like if we had 1x plus 0.5x, I could combine that to be 1.5 times x. What I'm going to do is just going to help with our notation. I'm going to do that same thing. So I could write this as 1.5 times 100. And the idea is that I'm taking 150% of 100. So by taking 100%, I keep that original value and then adding on 50%. So I'm going to keep using that notation for our calculation. So for year 2, what I want to do is take that last value, because it's that's going to increase by 50%. It's not going to increase by the same amount each year. It's increasing by 50% of our last value. So what I want to do is add on 50% of 150. So I'm doing is taking 1.5 times 150. Or how I could also write that is actually, let's see, that 150 came from 1.5 times 100, and now we're taking 1.5 of that 1.5 times 100. So really I have 1.5 squared times 100. This is going to get us to our exponential piece. So this calculation right here, so 150 plus half of 150 is 225. Let's look at one more here. When we get to year 3, now that we're kind of seeing a pattern, it's like I want to take 150% of that 225, which came from 150% of 100. So what I'm doing is it's like I'm layering on this multiplication by 1.5. So what we would have is 1.5 times 1.5 times 1.5 times 100. Or for short, 1.5 cubed times 100, which would be 337.5. All right, so in terms of a calculation, what we can do is see how the year that we're working with, specifically year 1, 2, and 3, are coming through as the exponent on that 1.5. So that 1.5 came from the percentage, this idea of 100% plus 50%, so that we're increasing by 50%. And then we have the exponent is changing based on how many years have passed, because it's basically determining how many times do we want to be taking that 150%. And then we're always multiplying by 100 because that's our initial value. Now, all I'm going to do is go through and just switch the notation around so that it's 100 times 1.5 to the 1 power, 100 times 1.5 squared, 100 times 1.5 cubed, because that will match our exponential growth form. So our exponential form, we're going to be able to see our initial value, and we're also going to see the percentage, in this case, of growth. It could also be decay. But in terms of an equation, we could calculate this amount of stores for company B is coming from 100 times 1.5 to the power of x. And what we're seeing here is that that 100 is our initial value, and the 1.5 is representing a growth by 50%. And to express that as a number, it's thinking of it as 1 plus 0.5. Okay, so that's our difference between linear and exponential. Linear is always adding the same amount on, as in this case, as time is passing. With this one, it's based on a percentage of the previous number, and with that, we start layering multiplication, which to shorten multiplication is where exponents comes in, and that's why we get this exponential function. Okay, so down here I wrote 2 different forms for writing our exponential growth and exponential decay functions. They do the same exact thing, it's just kind of how you prefer to do it, or sometimes the wording of the problem, one's a little more direct than the other, but really they come down to the same idea. So this first one, we have a times, and then this 1 plus r to the power of x. So as we talked about up above, a is our initial value, r is called our growth or decay rate, and then x is the number of cycles typically in time that have passed. So if we take that format to up above, what it would look like in this form would be that b equals, so a, our initial value would be 100, and then this 1 plus r, so our growth rate is It's growth because it's increasing, so it's a growth rate of 50%. So what we would see is a 1 plus 0.5 in those parentheses, and then our exponent is the unknown x, which is the number of years that have passed. This second form just carries out the addition or subtraction that's going to show up in the parentheses there. So the shortened form is a times b to the power of x. So a is the initial value. B is called the growth or decay factor. So what we would see up above there would be this growth factor of 150%, or 1.5. So it's just combining the 1 together with that value. And that's where we get this relationship that b is equal to 1 plus or minus r. It's addition when it's growth, it's subtraction when it's decay. Okay, so there's our two forms. I typically end up with this a times b to the power of x just because it is a simplified form, but at the root of it is that form that's coming from number 1 up above there. Okay, so what we want to do here is find an equation that would give the input and output pair shown in the table below. And with that, what we're going to do is evaluate how x and y are changing together. So mixed in here, there's linear and exponential, so we want to be able to tell the difference between those. The main difference will be that linear functions are changing by addition. We're adding on something each time. And with exponential functions, what we're doing is we're multiplying by something each time. So that's our main difference. Addition, subtraction with linear, multiplication, division with exponential. All right, so this first table, I have x is -2, -1, 0, and 1, and then y is -9, -5, -1, and +3. So with x, all I really want to do is, I just want to check that it's changing by the same amount each time. So let's see, -2 to 1 is adding 1, -1 to 0 is adding 1, 0 to 1 is adding 1. Okay, that change in x is staying consistent. Now that I know that, I'm going to focus on how we get from one value of y to the next. And what I want to do is find a theme. So I'll start with going from -9 to -5. I could add 4. And then what I want to see is, so we see addition coming through here, which would suggest that it's linear. But for it to be linear, that change has to be the same. How y changes with respect to x has to stay the same across the entire table. So -5 to -1, we could also add 4. And -1 to +3, we could also add 4. So because it's always adding something, this would be linear. And if I wanted the equation for it, what I would use, so I have this coordinate 0, -1, so that would be my y-intercept. So that's my value for b. And then for the slope, we take our change in y over change in x, which we saw our change in y is 4, change in x is 1. So I'm getting a 4 over 1 for the slope. So this would be y equals 4 times x, and then b is the -1. So 4x minus 1. Okay, let's go to this one. Let's go to the one with the fractions. I bet you were hoping I would save it for last, but I didn't. What I'm going to do is change these to improper fractions. So for x, we have 2, 3, 4, 5. I'm just going to do that quick check that x is changing the same each time. So like it's always adding 1. So that's good. But now I want to see how y changes, and to do that, instead of dealing with these mixed fractions of 1 1/3, I'm going to change them to improper fractions. So 1 1/3 is the same thing as 4/3. 2 2/3 would be the same thing as 6 + 8 over 3. And then 5 1/3, 15 + 1 over 3, so 16/3. 10 2/3, 30 plus 2, so 32 thirds. All right, so now let's evaluate how it's changing. And what we could do is we could start by seeing if we could get addition to work. But let's see what would happen if I used addition. So 4/3 to 8/3, I would have to add 4/3. 8/3 to 16/3, I would have to add 8/3. So the addition changes. So it's not linear. What I could see though is in the numerators, if I just kind of ignore the denominators, we go 4 to 8, 8 to 16, 16 to 32. And that is coming from a multiplication by 2. So if we multiply by 2, multiply by 2, multiply by 2, we can get our entire table there. So with that, because it's multiplication, this is going to be exponential. So setting up our exponential function, we need our initial value and we need this growth factor, which actually this multiplication by 2, that would just be our growth factor. So in terms of our function, a times b to the x, in this case, b is equal to 2. So that number that we're multiplying by, that would be our growth factor. To get the initial value, what you'll notice is that x equals 0 isn't on this table, but what we could do is we could find it, basically going in reverse on our table. So I'm going above the 2 and 4/3. What I'm going to do is kind of go backwards, look at x equals 1, then get to x equals 0. So if moving down the table, we're multiplying by 2, that means to go in reverse, we would divide by 2. So if I wanted x equals 1, I'm going to take that 4/3 and divide it by 2, which is 2/3. And then if I wanted to go back one more, so I'm at x equals 0, take that 2/3, divide it by 2, and that's a 1/3. And that gives us our initial value. So when x is 0, we would have 1/3 coming through on our table. So our function, initial value of 1/3 times the growth factor of 2 with an exponent of our variable x. All right, 2 more here. So we have a table with a -1, 1, 2, and 6 for x, and 3 halves, 5 halves, 3, and 5 for y. So let's see how x is changing. So x goes from -1 to 1, so that's adding 2. Then we go 1 to 2, and that's adding 1. And then we go 2 to 6, and we're adding 4. So it's all over the place in terms of how x is changing. So we just want to keep that in mind, of that x is kind of jumping around. And in fact, what am I going to do? What I'm going to do is -1 and 1 are close to using steps of 1. I'm just missing x equals 0. So I'm going to sneak that onto the table there. Let's think about if x was equal to 0. Maybe we'll wait for that. Let's wait for that. Okay. Let's just leave it, change in 2, change in 1, change in 4 for x. And then let's just look at y, and then we'll see how those pieces come together. So to get from 3 halves to 5 halves, we could add, let's try addition first. We could add 2 halves. To get from 5 halves to 1/3, that would be adding 1 half to get to 6 halves, which simplifies to 3. So what we could do here is, so that jump of 1 half is coming when the change in x is 1. So up above here where we had the change in by 2 units for x, it's like we doubled that step, which we're seeing. We saw addition by 2 halves, which we could think of as adding a half. And that should get us to that step where we're getting x equals 0. So there's probably this middle step, 3 halves, 4 halves, which is 2. But then what we did is we added a half again so we could get to 5 halves. And then to get from 5 halves to 1/3, we added 1 half. So now let's see if it works that if we add on, so what, from x equals 2 to 6, we had 4 jumps. Let's see if we're starting at 3, if we add 1 half 4 times, which is the equivalent of adding 2, we get to that value of 5. So what we're seeing here is that when the change in x is equal to 1, the change in y is equal to 1/2. We just needed to be careful because of those different jumps that were occurring. So that gives us our slope, and this is linear because it's working with addition. So linear, we have our slope of 1/2, and we found our y-intercept at 0, 2 by finding that spot in between. So this is going to be a function of 1/2 x plus 2. All right, last one here. This one, it has 0, 5, so we have our initial value, whether it's a y-intercept or, well, I guess there are y-intercepts for both. Whether it's linear or exponential, 0, 5 is going to be helpful. And then for the jumps in x, let's see, -2 to 0, we're going up by 2, 0 to 2, we're going up by 2, and then 2 to 3, we're going up by 1, so we'll just want to pay attention to those different jumps in x. But let's see, so in terms of addition, basically as soon as I see these fractions with different denominators, I know it's not going to be addition, because addition and subtraction shouldn't be changing denominators all that much, especially in the most simplified form. So with that, I'm thinking multiplication or division. So but you could really see it to get from 45 to 50, or sorry, 45 to 5. If I tried using addition and subtraction, I would subtract 40. Then to get from 5 to 5/9, subtracting 40 isn't going to do it. So it's not linear, and what we need to see is there's something that we can multiply or divide by with each of these that stays the same, just keeping in mind that last jump will be a little different because we're using a different step in x. So 4/5 to 5, what we're doing is a division by 9. So it's division by 9. What I want to do is think about that in terms of multiplication though. So this is multiplication by 1/9. And then if I have 5 to get to 5/9, that is also multiplication by 1/9. Now what we could see is going from 5/9 to 5/27, this is multiplication by 1/3, and this is better. This is a better view because this is when our x, the step for x, is equal to 1. So all these ones up above, we're combining 2 steps. So really there's this separation of multiplying by 1/3 times 1/3 and multiplying by 1/3 times 1/3, but really each single step is this multiplication by 1/3. So the multiplication division stays the same, so this is exponential. And in terms of a function, what we'll have is we have an initial value of 5, so I'm going to go 5 times, and then this isn't a growth factor, this would be decay, because our y values are going down. So that's where we're going to see a fraction in here, so times 1/3, and then that's going to be raised to an exponent of x. So in table form, that's how these different functions can come through. Specifically with exponential, we're looking for something we can multiply or divide by.